Okay, welcome back, everyone. Our next speaker is Schoute, who will be talking to us about surface code compilation via edge-disjoint paths. Take it away.
Thank you for inviting me to give this talk. Unfortunately, I couldn't attend, but hopefully this online experience will do it justice. And this work is in collaboration with Michael and Vadim at Microsoft. So to start off, you may know that faults become a certainty in large computations, which is why we have designed fault-tolerant quantum computations. And one way to do that is by using surface codes. And surface codes have a few very nice properties, such as that they consist of 2D local operations, they have a high error threshold, and we can perform lattice surgery for fault-tolerant logical interactions. And on the right, we see, say, one surface code patch, which encodes a logical qubit. So how can we make an architecture, or how can we make multiple logical qubits out of these patches? Well, we just tile them in the plane. So we take our patches and we, flip them horizontally or vertically, and tile this pattern in the plane. And we call this the surface code architecture. So now the problem that we study is what we call the surface code compilation problem, which is to minimize the cost of implementing some quantum algorithm on the surface code architecture. And in particular, we focus on the logical spacetime cost. And we note that the physical spacetime cost is monotonically related, which is simply the circuit depth times the circuit width, which is some measure of the volume of our computation in spacetime. So on the surface code architecture, we can define various elementary logical operations. For example, we have the operations of X and Z state preparation, so single qubits X and Z state preparation, single qubit measurements, which is the Z or this X measurement. We can perform Hadamard gates, which require 3 ancilla patches. So we have our Hadamard here and 3 ancilla. We can perform Bell pair preparation, which is depicted by this B and these 2 B's on adjacent patches, Bell measurement, and a move operation, which moves a logical qubit to an adjacent ancilla qubit in kind of a teleportation sense. And just to reiterate, this is still the surface code architecture, and every square here is one of our logical qubits. It's a surface code patch. Yeah, and associated with these operations is a depth, because we are still interested in the space-time cost. And in fact, the single qubit operations, such as state preparation and measurement, they have a depth cost of 0. So they're logical time steps we can implement in negligible time. The 2 qubit operations are all cost a depth of 1, and our Hadamard operation is actually the most expensive one, which has a depth of 3. Okay, so these operations might be somewhat unfamiliar to you, so let me relate it to some of the key circuit components that you are more familiar with. So for example, we can implement a CNOT gate with the following identity. If we have our source and target qubits and an ancilla patch prepared in the state plus, then this circuit will perform a CNOT operation between the source and the target qubit. And if we have a swap gate between a patch on A1 and B2, then we can implement that by performing this sequence of move operations, which will respectively move the logical qubit from A1 to A2 and B1 to B2, and then A1 to B1, etc. And we can see if we just count the depth of these circuits that both have a depth of 2. So now let's kind of zoom out a little bit, and we take our quantum algorithm, and this consists of many single qubit operations and C-naughts. Like we choose this gate set. So for example, Clifford plus T. And then we realize, oh wait, implementing a long-range C-naught can be quite costly if the two qubits storing the logical information are very far apart. If we use these sort of traditional swap-based techniques. So if we have 2 qubits separated by a distance k, then this results in a depth circuit of lower bounded by order k, which is the distance between these 2 qubits. Now, of course, we're able to do more than just swaps on the surface code architecture. And measurement and feedback in particular is quite natural and results in a constant depth circuit to implement a long-range C-naught. And in particular, it consists of preparing a long-range Bell state followed by a C-naught identity. So we know how to implement a C-naught using a Bell state as ancilla pair. Now, an additional ingredient that we need is that we are able to perform T-gates in this Clifford plus T gate set. And we assume that we can perform these T-gates at the boundary. That is highlighted here in red. So these red patches here are the boundary. And this is motivated by sort of separating the concerns of the computation from that of magic state preparation. So we kind of assume that there's a bunch of magic state factories pumping out magic states that are available at the boundary and with which we can fault tolerantly implement these T-gates. And the problem that arises is that we now need to entangle the bulk of our architecture, of our computational architecture, with the boundary to perform these rotations. So you get these long-range C-naught operations. So let me give a quick overview of the results that we will present. And we will present EDPC, the edge-disjoint path compilation algorithm. And EDPC is able to compile singular C-naughts in constant depth, as I've showed before, whereas swap is lower bounded by the diameter, which is square root n. But as well, we're able to compile n over 2 parallel C-naughts, so one slice of n over 2 C-naughts in a depth of square root n. And finally, if we take k parallel rotations, so say k T-gates, we're able to compile that to a depth of square root k. Now, if we compare that to a traditional, another traditional approach, which is sequential poly-based computation, then this approach does not experience an overhead from Clifford circuits at all, which is why we say, okay, the cost here is 0. However, it is quite slow when you have a lot of T-gates in your circuit. And in fact, the depth is lower bounded by order k. And yes, you can scale up or scale down the number of ancillas that you use, but then the depth will, the space-time cost will sort of stay the same. So in this case, sequential poly-based computation, we believe is still gives the right characterization. All right, so let's see some of the details. Yeah, so first, let me show you how to implement a C-naught via Bell states. So if, say, we have a Bell state on 2 ancilla, B and C, then we can implement a C-naught operation with this following identity. And now the simple ingredient to performing long-range C-naught operations is this long-range Bell state preparation, which we can perform using this identity. So we perform a Bell state preparation, and then we perform sort of a teleportation of the second qubit to the fourth line. And we can simply iterate this construction to perform long-range Bell state preparation at arbitrary distance and depth 2. And therefore also perform CNOT operations in depth 2 at long range. What this looks like on the surface code architecture is, in the first phase, we prepare a bunch of Bell pairs along a path P, and then we consume these Bell pairs to prepare a long-range Bell state and perform a ZZ and XX measurement at the end. And this gives us the ability to perform parallel CNOT operations in depth 2, as long as all paths P are vertex disjoint. And with that, I mean that these paths P will not intersect at any vertex. All right, so our contribution is actually to make this slightly more powerful. So to do that, we first need to assume a 1:3 data qubit to ancilla ratio. And remember, we will account for that in the space-time cost, because our space has now blown up by a factor 2. And we show in the paper that we can actually execute all CNOTs that are connected via edge disjoint paths in depth 4. So the vertex disjoint path was depth 2, but the edge disjoint paths was depth 4. So here on the right, we have a figure of a bunch of CNOT operations that are connected through paths that are all edge disjoint. So in particular, if you look at a vertex here, then the orange line and the green line do not share an edge. They only share a vertex, which is allowed. And the high-level idea is to fragment these edge disjoint paths in the sense that, which is a technical term we introduce, we fragment the edge disjoint paths into 2 vertex disjoint paths. So we take our edge disjoint paths and we assign them to two different vertex disjoint path sets. We do that by labeling each crossing with 1 or 2, which gives us these 2 fragmented vertex disjoint path sets. So we can see that the paths on the left and on the right are both vertex disjoint, and if we if we connect these paths together, then we will get back our original set of paths that we wanted to implement. So all that remains is the circuits that we need to implement along these paths, which we provide in detail in the paper. So for example, a path that originates from a control in the first phase has a circuit that looks like this. And similarly for all the 5 other possibilities. So, yeah, I'll skip over the details here, but you can believe me that they're in the paper. All right, so, okay, now we have 2 ways to implement long-range CNOTs, in particular long-range parallel CNOTs. And one way is to perform these CNOTs along vertex disjoint paths in depth 2. And the other way that we can contribute is that we can perform CNOTs along edge disjoint path sets in depth 4. So why do we actually prefer edge disjoint paths, right? Because the depth is higher and we need these we need a lot of ancilla. Well, we believe that, well, it's kind of easy to see that if we can connect more ends of CNOTs by paths, then this will result in more CNOTs that are executed. So therefore, if we can find a larger set of paths, then we can execute more CNOTs. And in fact, the maximum edge disjoint path set size is always as large as a vertex disjoint path set, because an edge disjoint path set, because a vertex disjoint path set is an edge disjoint path set, but not vice versa. And there are actually examples on the grid that give a square root n separation between these 2. So there's an example where we're able to find an edge disjoint path set of a size of square root n, whereas the vertex disjoint path set is at most of size 1. So this gives an asymptotic advantage for edge disjoint paths. Moreover, if we want to approximate the maximum vertex disjoint path sets on grids, then this is much harder than edge disjoint paths. In particular, for vertex disjoint paths, we know that approximating this up to subpolynomial factors is hard. It's inapproximate. There's an inapproximability result under certain hardness assumptions. Whereas for edge disjoint path set, in 95, we know, since 95, we know logarithmic and constant factor approximation algorithms. Now there's one caveat. We're actually not dealing with grids for this edge disjoint path problem. We're dealing with what we call this operator graph, where you kind of have a grid, but it has holes for these data qubits, and we want to connect control qubits to the target qubits in particular, which is why you get these directed edges. And this operator graph is therefore slightly more constrained. However, we're able to use a greedy square root n approximation algorithm, which is obviously not a great approximation factor, but in practice it performs fairly well. But it seems fairly straightforward to adapt this logarithmic factor approximation algorithm to this operator graph by Alman and Rabbani. And if we can answer this question of finding edge disjoint paths on this operator graph to some kappa approximation factor, where we note that kappa is order 1 on the grid, then this implies that we can implement a set of parallel C-naughts, which we denote by this calligraphic T, can be optimally compiled up to a factor of order kappa times log T. So if this kappa is this logarithmic factor, as this approximation algorithm would suggest, we can implement a set of parallel C-naughts up to polylogarithmic approximation in the depth. Okay, so maybe you've zoned out a little bit, so let me, we're gonna zoom out a bit and complete our gate set with T gates. And additionally, there's also HSH and HDH gates. And with these gates and C-naughts and Clifford operations, we're able to complete our gate set. And we had assumed that we can perform these gates at the boundary, if you recall from the introduction. And a simple gadget that we used to perform these T gates, so Z theta is a rotation around the Z-axis for an angle theta, and T is theta pi over 4, I believe. Then if we want to implement an arbitrary rotation around the Z-axis, we can implement it through this gadget, where this 0 qubit is an ancilla that we assume is on the boundary. So all we need to do is kind of entangle this ancilla qubit with our bulk qubit through a long-range C-naught operation. Then we are able to perform our T-gate by our earlier assumption on the boundary, and we can teleport the result back into the data qubit. And similarly for HTH and S and HSH. Yeah, so this therefore reduces implementing these rotations to a problem of solving edge disjoint, of finding edge disjoint paths. And in fact, this problem is easier than for arbitrary C-naughts, because we can find the maximum edge disjoint path set for this particular problem by solving a max flow problem, which is easy by this Ford-Fulkerson algorithm. So we can find the optimal or the maximum EDP set. And this gives us a very simple greedy algorithm for implementing parallel rotations. So if we have a set of parallel rotations, which is this calligraphic G, then what we're going to do is, until this set G is empty, we're going to execute the maximum set of remote rotations as given by this max flow solution. And then we're going to execute them and remove them from the set. And we iterate this until the set is empty. And we can prove that this actually executes all rotations in the set calligraphic G in a depth of square G. And the proof is very simple. It's just 2 lines, or the idea at least. And we can kind of see that if we have a rectangle on this grid, then the boundary of this rectangle is at least of size square root G, which is equivalent to the min-cut size. And by this max flow and min-cut equivalence, as shown by this Ford-Fulkerson again, we need at most square root G rounds. Okay, so if we put all the pieces together, we get our EDPC algorithm. So let's say we are given a circuit C where we have commuted all the Pauli operations to the end. Then first, for the available operations in a layer in our circuit, we're going to execute all the single qubit operations first, including Hadamard, which can take a depth of 3. Then we're going to execute the k available rotations in depth at most square root k, as we saw on the previous slide, which gives us the order square root k performance for parallel rotations. And finally, we're going to execute the long-range CNOT operations in our circuit by using this approximation algorithm for the number of for maximizing the number of edge disjoint paths given this set of C nodes. So yeah, just in summary, EDPC will then therefore compile k parallel C nodes or k parallel rotations to a depth of theta square root k, because we have an upper bound of square root k and a lower bound of square root k, and a set of parallel C nodes to a depth of theta square root n. Right. So yeah. So to remind you, the objective of these compilation algorithms, these surface code compilation algorithms, is to minimize the space-time cost of the compiled circuit. And our EDPC algorithm has a fairly high space-time cost, where we have 3 ancilla qubits per data qubit. And we compare this to a swap-based approach, where we simply route the qubits to the boundary that need to do these T gates or HTH gates. And this approach has a lower space cost. And as a quick summary of swap-based routing, we're able to perform arbitrary permutations on grids with swaps with a 1-to-1 data to ancilla qubit ratio on this rotated grid, where we first route along the columns or along the rows, and then along the columns, and then along the rows again, in a depth, in a space-time cost that scales as 4 times L1, which is the rows length, plus 2 times L2, which is the column length. So this scales as square root n, order square root n on the grid. Yeah, so if we have a set of parallel CNOTs that we sample at random, then we plot some of our benchmarks here for various densities of these parallel CNOT circuits. And the density here is given by this n CNOT parameter, by which we mean that if n CNOT equals n, then we have n qubits involved in performing a CNOT. And if n CNOT is 0.1 n, then 10% of all qubits are involved in performing a CNOT, etc. So in the case where all qubits are performing some CNOTs and where we sample at random how we pair them up, we see that there's already a small advantage for this EDPC approach if we consider larger and larger grid sizes. And additionally, our algorithm is much faster in classical computational cost, which is why this curve here ends so early, because it's just very slow to compute. Now, if we reduce the densities, we see a markedly large improvement, actually. So if we only have 10% of our qubits performing CNOT operations, then we have these the squares here, this line, and in the white line we have EDPC. And for large grid sizes, we can kind of see already that there's maybe factor 2 or 3 improvement in the space-time cost. And finally, if we consider very sparse parallel CNOT circuits, so where square root n of all the qubits are performing a CNOT operation, then we know by our lower bounds that the swap-based implementation is lower bounded by square root n, whereas the EDPC algorithm could actually approach a constant space-time cost. And we might be able to observe that here, but I was not willing to make that claim in the paper. Okay. So so another benchmark that we looked at was a generalized Toffoli operation, which is the multi-controlled CNOT gate, which we denote by C to the K naught. We actually only consider the first half of this operation, so only so not the uncomputation part, which is usually implemented through measurements and feedback, and some technical limitations prohibited us from making that comparison fairly with the swap-based approach. So the circuit that we're interested in is this half C to the K naught circuit, and in here we pick K to be equal to 8, and this is a fairly standard circuit which will apply an X rotation on this final qubit if all the controls are 1. Yeah, so if we compile this to the grid, then we see that the space-time cost of this circuit initially for the swap-based approach is actually better. So for circuit sizes for grid sizes up to 64 qubits or so, we see that the space-time cost for swap-based approaches is actually better. However, in this log-log plot, we see that the asymptotic scaling for EDPC is much better than the swap-based approach. So the exponent of the polynomial is lower in this log-log plot. Now, to conclude, we propose this edge-disjoint path compilation algorithm, which compiles Clifford plus T circuits to the surface code architecture. We looked at some of the benchmarks and have seen that this EDPC approach has shown certain improved performance for what seems like relevant circuits. And we have also shown various improved asymptotic upper bounds for this surface code compilation problem. Now, some of the future work that we're considering is, I mentioned this briefly in the middle of the talk, we need this approximation algorithm for edge-disjoint paths on the surface code architecture, or this operator graph in particular, because that would give improved theoretical upper bounds. Unfortunately, the algorithms that are usually involved there in the classical literature have very large constant factor overheads. So in practice, this might not be that useful unless we have very large systems. And as a throwback to Drew's talk yesterday, we can also consider integrating this compilation problem together with a routing problem. So there's a trade-off between when we want to perform long-range gates and when we might prefer to permute our qubits first, and then perform the gates locally, which might help us in the long run if we have some sequence of gates that are all clustered in some sense. So yeah, and in fact, if we have measurement and feedback, we can perform long-range teleportation to permute these qubits. So you exactly fit into this LOCC routing framework. And the final note that is kind of interesting is that if we have a diagonal gate D, then we can implement this diagonal gate D at the boundary through performing a bunch of long-range CNOT operations, implementing the diagonal gate D, and then teleporting this gate back into the logical qubits. So, for example, this could be useful to implement a CCZ gadget, for example, which is in particular useful for classical oracles, for example. So yeah, thank you for listening, and feel free to ask any questions.
Thanks for a great talk, Eddie. Do we have any questions in the interest of time? Maybe just a couple? Any? Yes, Sam.
In your last slide there, about the diagonal gate performed remotely, you're performing the gate after entangling it with your existing data qubits. What happens if you have sort of something like where with key state distillation, where you would have to perform the gate before you do that entanglement?
So in case you didn't hear that, the question was what happens if you, oh my gosh, I've forgotten. If you perform the measurement before the entanglement?
The gate, like the diagonal gate D.
If you perform D before the entanglement.
I see. So this identity follows from commuting this D gate through these CNOT operations, right? But if you commute this D gate through the CNOT operations, then I think it would end up over here, not on the ancilla qubits, right? So let me think. Is that correct? Actually, yeah, maybe this is a good question. What happens if you perform the D gate before? Is there a particular application that you're thinking of?
With T-state distillation, I thought you would have to kind of create these resource states by applying the gate to, say, a superposition, and then inject that in your code. And here it's sort of like you apply the CNOTs, and then you apply this gate to those extra qubits.
Yeah. Yeah, so I can imagine you might have some research. You could, if this D could be performed before performing the CNOTs, then you have just some resource state here, and you don't need to do some state injection to implement this D gate after the CNOTs. So it might actually, it might be easier to implement that way. But I'm not sure you can do it.
Thank you, Eddie. Sorry, in the interest of time, we might move on. So if everyone can thank Eddie again for a great talk.